What if the oldest spacecraft still speaking to Earth suddenly went silent at the exact moment it was rewriting what we know about the edge of our solar system? What if the scariest part was not the silence itself, but the fact that nobody on Earth could do anything fast enough to save it? If stories like this make you feel the universe get bigger, tap like, subscribe, and share this with one person who still looks up at the night sky and wonders what is really out there. On July 24, 2023, something small happened very far away. On paper, it looked almost harmless. A routine set of commands was sent to Voyager 2, a spacecraft NASA launched in 1977. The command sequence should have been ordinary. It should have been one more quiet maintenance step in a mission that had already lasted longer than almost anyone thought possible. Instead, one wrong instruction nudged the spacecraft's antenna just 2 degrees away from Earth. 2 degrees. That is the kind of number most people ignore. But in deep space, tiny numbers can become giant disasters. Voyager 2 was not circling Earth. It was not near the moon. It was not even near Pluto. It was more than 12 billion miles away, farther than almost anything humans have ever built, has any right to still be working. At that distance, Earth is not a big bright target. It is a speck, a direction, a whisper of a home the spacecraft has been trying to face for nearly half a century. So when that antenna moved 2 degrees off target, the link that tied Voyager 2 to humanity nearly snapped. And that is what makes this story feel less like a technical glitch and more like a scene from a survival film. Because Voyager 2 was not dead. Engineers could still detect a weak carrier signal, a bare electronic heartbeat. The spacecraft was alive. It just could not truly hear us, and we could not properly hear it. It was like standing on opposite sides of an ocean in a storm, knowing the other side still exists, but losing the words. The worst part was the clock. Radio signals move at the speed of light, which sounds fast until you're talking to something this far away. A command from Earth took about 18.5 hours to reach Voyager 2. If the spacecraft answered, its reply took another 18.5 hours to get back. One question and one answer cost 37 hours. That means every guess mattered. Every test mattered. Every mistake lasted almost 2 days. There was no joystick, no live feed, no instant fix. Just a small team at NASA's Jet Propulsion Laboratory, staring at screens, thinking about a machine built before many of them were born, and trying to rescue it across a distance so large that human language almost breaks when we describe it. To understand why this moment mattered so much, you have to understand what Voyager 2 really is. Most spacecraft are built for a target, a task, a window of time. They launch, do their work, and fade into history. Voyager 2 refused to live that kind of life. It launched on August 20th, 1977, during a rare planetary lineup that gave NASA a once-in-many-lifetimes chance. The giant planets were arranged in a way that let one spacecraft use gravity like a chain of slingshots. Jupiter could throw it toward Saturn. Saturn could redirect it toward Uranus. Uranus could help send it to Neptune. It was a path so valuable because it would not come again in the same way for generations. Voyager 2 took that path and did what no other spacecraft has ever done. It became the only probe in history to visit all 4 giant planets up close. It flew past Jupiter and Saturn. Then it kept going. It became the first human-made object to visit Uranus. Then it kept going again and became the first and only spacecraft ever to fly by Neptune. It discovered new moons, new rings, strange weather, and worlds that looked less like distant dots and more like real places. Then, after the grand tour was over, the mission should have been ending, but Voyager 2 did not end. That is what makes the Voyagers so hard to explain to people who only know space missions as headlines. These spacecraft did not just survive, they kept becoming more important. What began as a planetary mission turned into something even rarer, a chance to study the outer skin of the sun's influence itself. Our solar system does not end at Neptune. It sits inside a huge bubble created by the sun. That bubble is called the Heliosphere. The sun constantly throws out a stream of charged particles called the solar wind. That wind pushes outward in all directions, carrying the sun's magnetic influence with it. For a very long distance, that solar bubble helps shield us from part of the harsher radiation coming from the galaxy beyond. But the heliosphere is not endless. At some point, the pressure from the solar wind meets the pressure of interstellar space, the space between stars. The boundary where the sun's outward influence gives way to that wider galactic environment is called the heliopause. For decades, scientists built models to describe what that edge should be like. They imagined transitions, layers, gradual blending, a kind of fading border between one environment and another. Then Voyager 2 went there. But before we get to what it found, go back to that July mistake in 2023, because now the stakes look very different. This was not just an old spacecraft that still had sentimental value. This was one of only 2 human-made objects ever to operate beyond the heliosphere. And Voyager 2 had something its twin did not have at the most important moment. Voyager 1 crossed into interstellar space first in 2012. That was historic. But one of its plasma instruments had stopped working long before the crossing. Scientists still learned a huge amount from Voyager 1, but they did not get every kind of direct measurement they wanted. Voyager 2 was different. When it approached the boundary in 2018, the right instruments were still alive. It could measure the plasma around that crossing in a more direct way. That made Voyager 2 more than a backup. It made it the spacecraft that could test the big assumptions. So when its antenna drifted off Earth in 2023, NASA was not only trying to save a signal, it was trying to protect one of the only living scientific witnesses we have in interstellar space. At first, the options were terrible. The safe option was to wait. Voyager 2 had an automatic reset built into its system that was expected to point the antenna back toward Earth in mid-October. That was the backup plan. But waiting until October meant losing months of unique data from a spacecraft drifting through a place no other operating mission can reach. The risky option was to try to hit Voyager 2 with a command anyway, even though its antenna was off target. NASA hoped a powerful enough transmission might still get through. That hope rested on the Deep Space Network, one of the least famous and most amazing systems humans have ever built. It is a global set of giant radio antennas placed in California, Spain, and Australia. Those 3 locations are spread around Earth so that as our planet turns, at least one station can keep listening to spacecraft in deep space. The public rarely talks about it. Movies barely mention it, but without it, many of our greatest missions would become silent monuments in the dark. And for Voyager 2, one station mattered most: Canberra, Australia. Because Voyager 2 is traveling in a southern direction relative to the solar system's plane, the Australian station had the best line for the job. First, NASA listened. On August 1st, engineers detected Voyager 2's carrier signal. That did not restore communication, but it changed everything emotionally. The spacecraft was still there, still alive, still moving along its expected path. Now came the gamble. On August 2nd, NASA sent what officials themselves called an interstellar shout. A 100-kilowatt command blasted from Canberra toward a spacecraft more than 12.3 billion miles away. The message was simple: turn back toward Earth. And then came the wait. Not the normal kind of waiting, where you pace for a few minutes and check. A screen. This was the kind of waiting shaped by physics. 18 and a half hours for the command to arrive. Then, if all went well, another 18 and a half hours for confirmation to return. Roughly 37 hours with no way to speed anything up. Imagine being on that team. You have spent years learning the quirks of a spacecraft older than the modern internet. You know every move could be its last. You know a wrong signal might do nothing, or worse. You know silence after 37 hours might still not mean the mission is gone, because timing can drift and nothing out there happens on your emotional schedule. So you sit with a kind of helpless discipline, you wait for physics to finish, and on August 4th at 12:29 a.m. Eastern Time, Voyager 2 answered. Science and telemetry data began flowing back to Earth. The antenna was pointed home again. The spacecraft was operating normally. The interstellar shout had worked. Think about the scale of that sentence. A radio command left Earth, crossed more than 12 billion miles of space, reached a machine the size of a small car, persuaded it to turn, and then its answer crossed that same abyss back to us. The rescue feels almost impossible until you remember that impossible is often just a word we use before engineers quietly solve something. And yet, as dramatic as that recovery was, it is not the deepest part of the story. The deeper part is what Voyager 2 was able to keep telling us after it came back. If you're still with me, you're exactly the kind of viewer this channel is built for. So take 5 seconds right now. Hit subscribe, send this video to the smartest person you know, and let them see whether they would have kept faith in a machine that had already traveled for decades beyond the planets. To see why Voyager 2's return mattered so much, we have to step back to November 5th, 2018, the day it crossed the heliopause. This was not a cinematic crossing. There was no glowing wall in space, no giant sign saying you're now leaving the solar system. What changed were the readings. The instruments saw the solar wind drop sharply. At the same time, cosmic rays from outside the Heliosphere rose. That told scientists Voyager 2 had entered a different environment. And then the real surprise began. 1 year later, 5 research papers were published together describing what Voyager 2 had seen at the boundary. That alone told you something big had happened. Scientists did not just get one interesting result. They got a cluster of them, touching plasma, magnetic fields, energetic particles, and the structure of the heliosphere itself. The first shock was the boundary's sharpness. Many models had suggested a broad transition zone, a blurry region, where solar plasma and interstellar plasma would mix over a long distance. Voyager 2 found something much more abrupt. The change happened over less than a day of travel time. In space terms, that is stunningly thin. Instead of a slow fade, it looked more like crossing a line. That matters because boundaries teach you how systems really work. A soft border suggests gradual mixing. A sharp border suggests stronger structure, stronger forces, and a cleaner separation than expected. In other words, the edge of the sun's bubble was not behaving like a gentle mist. It was acting more like a frontier. Then came the plasma data. Plasma is often called the fourth state of matter. It is gas with charged particles, and it fills much of space. Scientists expected the plasma beyond the heliosphere to be colder and denser than the plasma inside. Voyager 2 confirmed the density difference, but it also found signs that the plasma outside was warmer than expected. Not warmer than the plasma inside the heliosphere, but warmer than many predictions for local interstellar space had suggested. Why does that matter? Because temperature is not just a number, it is a clue. It tells you about pressure, motion, compression, and energy flow. If the plasma just outside the heliopause is warmer than expected, something about the interaction between our solar bubble and the galaxy around it is more dynamic than the simpler models assumed. And there was more. Voyager 2 found that the magnetic field just beyond the heliopause was aligned in a surprising way with the magnetic field inside the heliosphere. Voyager 1 had hinted at this earlier, but with one spacecraft alone, scientists could not be sure whether it was a cosmic rule or a strange coincidence. Voyager 2 confirmed it was real. The fields were more parallel than many expected. That is the kind of result that does not sound emotional at first until you realize what it means. Nature was under no obligation to match our neat diagrams. The universe could have twisted those fields any way it wanted. Instead, it revealed a structure we had not properly anticipated. That means our mental map was wrong. And when your map of the frontier is wrong, every conclusion built on that map becomes less secure. Voyager 2 also helped show that the heliosphere may be more porous in some regions than in others. Think of the sun's protective bubble less like a perfect steel shell and more like a moving vessel with uneven walls. In some places, energetic particles leak more easily across the boundary. In some directions, the shape and shielding seem different. Voyager 1 crossed in one region, Voyager 2 crossed in another. The two crossings did not tell the exact same story. That difference may be one of the most important parts of all. Scientists love more than one data point because one data point can fool you. It can make a local quirk look universal. Voyager 2 helped break that trap. It showed that the heliosphere is not a clean, simple bubble with identical properties everywhere. It seems shaped by its movement through interstellar space. It seems compressed in some places, more open in others, and more complicated than our textbooks once let on. So when people say Voyager 2 went silent and came back, changed everything, the change is not that the silence itself transformed science. The change is that the spacecraft returned in time to keep sending data from a place where the old assumptions keep failing. That is a much bigger story, because this is how science often moves forward, not through one grand speech, not through one perfect theory, but through embarrassment, correction, surprise. A machine goes to a place we have never been, and the place refuses to match our expectations. What makes Voyager 2 so moving is that it does this while also being unbelievably old. It runs on electricity made from the heat of decaying plutonium. It loses about 4 watts of power each year. Engineers have had to shut down instruments one by one to keep the mission alive longer. In March 2025, NASA turned off Voyager 2's low-energy charged particle instrument to save power. Before that, in September 2024, the plasma science instrument was turned off. As of 2026, Voyager 2 still has key instruments running, including its magnetometer, plasma wave system, and cosmic ray subsystem. That means the spacecraft is still useful, still measuring, still giving us real information from a place beyond the sun's bubble. But it also means the clock is always ticking. Every power-saving move buys time, not immortality. Each instrument shutdown is a decision made, with the knowledge that it may never come back. Engineers are not just operating a mission now, they are curating its last years, trying to stretch a fading machine long enough to catch one more clue, one more anomaly, one more beautiful contradiction. And there is a human side to this that matters. The people working on Voyager today are not the people who built it. Many were not alive when it launched. They inherited a spacecraft, a culture, and a set of engineering habits from another era. They test commands on old hardware. They work through strange legacy systems. They solve problems with patience because there is no second attempt that can be sent casually across nearly 20 hours of light travel time. Imagine caring for a machine built by another generation, using knowledge passed down like craft, while it travels farther from Earth every day. Imagine knowing that one typo, one wrong assumption, one badly timed command could end a scientific conversation that began before many modern careers, nations, and technologies took their present form. That is not just engineering. That is stewardship. And maybe that is why this story hits so hard. Voyager 2 is a machine, yes, but it is also a thread. It ties together the optimism of the 1970s, the planetary discoveries of the 1980s, the boundary-crossing science of the 2010s, and the quiet crisis of 2023 into one continuous line. Most human projects do not last long enough to become generational. Voyager did. It also does something rare in science communication. It gives us scale we can feel. People hear space numbers all the time. Millions of miles, billions of miles, light hours. They blur together. But the Voyager 2 silence forces those numbers into emotion. 18 and a half hours one way, 37 hours round trip, 14 days of uncertainty from a 2-degree error. Suddenly, distance is not abstract. Distance becomes stress. Distance becomes risk. Distance becomes the reason a tiny mistake can turn into a global rescue effort. Here's the part I do not want you to miss. The silence was scary, but the real message of this story is not fragility. It is reach. Humans built something in the 1970s that still talks to us from interstellar space. Humans built antennas on Earth sensitive enough to hear it. Humans sent a command across the void and got an answer back. And the answer was not just, I am alive. The answer was, your models are incomplete. That is incredible. If this story gave you chills, pause for 1 second and do something different. Drop a comment with one word that describes how Voyager 2 makes you feel. Then share this video with someone who thinks old technology cannot still change the future. There is also a deeper scientific reason this mission matters right now. Voyager 2 is not just telling us about one distant spacecraft, it is helping us understand the shield that helped make life on Earth safer. The Heliosphere blocks a large fraction of galactic radiation. That matters for planets. It matters for astronauts. It matters for future missions traveling far from Earth. The better we understand the heliosphere's shape, leaks, and magnetic structure, the better we understand the environment our solar system moves through, and that matters even beyond our own neighborhood. When we study other stars and ask whether planets around them may be habitable, we often focus on size, distance, and temperature. But a star's bubble of charged particles and magnetic influence may matter too. Protective space weather is part of the story of life. Voyager 2 is helping us understand the home version of that story in real time. So yes, the title sounds dramatic. Voyager 2 went silent. NASA got it back. What it found changed everything. But for once, the dramatic version is close to the truth. Because what changed was not every fact in astronomy. What changed was our confidence in some of our simplest pictures. The edge of the sun's domain is sharper than expected. The plasma behavior is stranger than expected. The magnetic geometry is stranger than expected. The heliosphere itself may be more uneven, more leaky, and more alive in its interaction with the galaxy than our earlier models suggested. And all of that comes from a spacecraft that should have been a historical footnote decades ago. That is almost poetic. Voyager 2 was built to visit planets. Now it teaches us humility at the edge of interstellar space. At some point, that teaching will end. NASA believes the Voyagers may keep at least one instrument alive into the 2030s, but nobody promises that timeline. Deep space is harsh, systems age, surprises happen. One day the remaining instruments will shut down, one day the radio signal will stop, one day Voyager 2 will keep moving, but it will do so in silence forever. When that day comes, the spacecraft will not be dead in the ordinary sense. It will still exist. It will still carry the golden record, a message from Earth placed aboard for any distant finder, however unlikely that meeting may be. It will keep drifting through the galaxy long after all of us are gone. But right now, it is still talking. That is the part that gets me. Not that humans once built something amazing. We did. Not that it traveled farther than almost anything else. It has. Not even that it survived a communication crisis in 2023 through a brilliant act of engineering. All of that matters. What gets me is that Voyager 2 is still in the middle of its final gift. It is still sending back truth from a place no human can visit, no telescope can fully replace, and no younger spacecraft is ready to reach anytime soon. It is still correcting our guesses, still warning us against easy pictures, still turning deep space from imagination into measurement. So the next time you hear someone say, space exploration is too slow, too expensive, or too far, removed from daily life, remember this machine. Remember that a spacecraft launched when disco was on the radio is still teaching us how our solar system meets the galaxy. Remember that when it went silent, people on Earth fought to bring it back, not for nostalgia, but because what it was saying still mattered. And maybe that is the real lesson. The universe does not give up its secrets quickly. Sometimes it takes decades. Sometimes it takes a machine that survives longer than its makers expected. Sometimes it takes a 37-hour wait just to learn whether your one desperate message got through. But when the answer comes, if you are patient enough, careful enough, and brave enough to keep listening, it can change the picture of where we live. Voyager 2 did not just come back from silence. It came back with evidence that the border of our world is stranger, sharper, and more alive than we thought. And somewhere tonight, beyond the planets, beyond the Kuiper Belt, beyond the edge of the sun's great bubble, that old spacecraft is still moving through the dark and still turning distance into knowledge, one faint signal at a time.